So I'm going to be going over a couple different problems from Chapter 7, which is on the periodic properties of the elements. Let me turn on my light here so that you can see what I'm writing as clearly as possible. And I'm going to begin with question number 15. Now, question 15 is actually conceptual, I believe, and it is talking about the outer boundary of an atom and why it's difficult to measure. Okay, because an exact outer boundary cannot be measured or even calculated for an atom, how are atomic radii determined? Well, atomic radii are really determined is that if you have two atoms that are bonding, like fluorine and fluorine, well, there's a point where we can measure the distance between the two nuclei. So if that's the nucleus and that's the nucleus right there, well, if you want to know the atomic radius, you find that distance, the distance between the two of them, divide by 2, and boom, you've got the radius. Simple as that. That's how atomic radius is determined. The difference between a bonding radius and a non-bonding radius is that a bonding radius, well, this is an example of it. It's when two atoms are bonding. A non-bonding radius is typically measured when you have gas molecules impact one another, and when they strike each other, you can measure the distance that way. So if it was fluorine, outermost electrons out here, then you would figure out its atomic radius when it collides with another gaseous molecule, if it's fluorine in particular. All right, now I'm going to jump to another question, which is 17. 17 is, heck, one of the more simple questions we have here. So 17 says that you have a distance between two tungsten atoms, and that distance is exactly 2.74 angstroms. And that question is asking for what is the radius? Well, take it and divide it by 2. Done. Let's see, I'll make sure my math is right. 3, 7, I believe. So that would be 2, 6. Yep, that's right. So that's the answer for that portion. This is, of course, called the bonding radius, but it's also referred to as the metallic radius because we're dealing with the element tungsten. All right, next question. Question 37. So on 37, I think we get to something a little bit more complex. It says, why are ionization energies always positive quantities? Well, that's actually a little bit more tricky to answer. Electrons have a negative energy because they're always being attracted by a nucleus. So say I have a nucleus of a hydrogen atom, and I have two electrons out here. So these electrons are being attracted by that positive charge. Oops, I should be drawing the arrow going that way. So in any case, you have, there's my really weird arrowhead, the answer essentially is that they're always positive quantities because it always takes energy to remove an electron from an atom. Electrons actually have what are referred to as a negative energy according to Coulomb's law when they're closer to an atom. That's not the important question. The real important question is that why does fluorine have a larger first ionization energy than oxygen? So if you look at the periodic table, let me get out a periodic table, and here's fluorine and here's oxygen. Why does fluorine have a higher ionization energy? Well, if you look at what the electron configuration is for both of these atoms, you're going to see that the electron configuration for fluorine is 1s2, 2s2, 2p5. For oxygen, it is 1s2, 2s2, 2p4. Okay, now we have to talk about effective nuclear charge. So let's go back and let's draw a picture of what's happening for both of these atoms. So for oxygen right here, we have a total of, let's see here, 8 protons in the center of it. So I'm just going to draw 8 pluses. And I'm not going to bother drawing all of the neutrons. They're there. There's, on average, about 8 in oxygen. But the nuclear charge is pretty much, Z is always going to be 8. Now for fluorine, the nuclear charge is not 8. It obviously has an additional proton. So fluorine's nuclear charge is 9. Now in terms of the electrons, they both have the same core electrons. So the core electrons are the electrons that are not valence electrons for both of these. Well, if I go back to the electron configuration up here, these guys, the 2s and the 2s orbitals and the 2p orbitals, these are our outer valence electrons. The 1s2, those are the core. So they both have the same core electrons, which are 2 electrons. Now, we should have learned that the effective nuclear charge, Z, which is the shield, is based on Z minus the shielding effect. Well, the shielding effect for both of these atoms are the same. S is exactly the same. But the number of protons is different. So for oxygen, the effective nuclear charge would be 8 minus 2, which is the nucleus, the number of protons, minus the core electrons. So for this one, the effective nuclear charge would be 9 minus 2. So the effective nuclear charge for oxygen is actually lower. For fluorine, it's higher. So what that means is that fluorine, if I'm comparing these two atoms right here, because fluorine has a higher effective nuclear charge, it has more positive forces pulling those electrons in. And because of that, those electrons are harder to remove. So the ionization energy for fluorine is higher than oxygen because fluorine is a smaller atom, and that's because it has a larger effective nuclear charge. And this is basically the positive pull from the nucleus on outer electrons. And don't forget, it's the outer electrons that are removed first when you're dealing with ionization energy. So that's the answer. I believe I've answered every component. Oh, the second answer is, why is the second ionization energy of an atom always greater than its first ionization energy? And that's on 7.37. Really, the second ionization energy of an element is greater because the effective nuclear charge is larger for the positive cation than for a neutral atom. More energy is required to overcome the effective nuclear charge. Well, what does this mean? If I have, say, I don't know, I have sodium and then I have sodium plus. If I'm comparing these two, then this one, the nuclear charge in comparison, the ratio between protons to electrons, is going to be, there's a heck of a lot more protons in relationship to the electrons. So the effective nuclear charge is slightly larger. The ratio of protons to electrons for a neutral sodium atom, that's not the case. So for sodium, when it's neutral, we've got 11 protons and 11 electrons. Here it's 11 protons and 10 electrons. These protons have a much stronger pulling force in comparison to all of the total electrons in an ion. Therefore, if I was going to remove a second electron from sodium and give it a 2 positive charge, that would require a heck of a lot of energy. And that's why you don't actually see that very often when it comes to charges of sodium. You really only ever see positive 1 because the second ionization energy is so high to create an ion out of sodium. That's too positive. Now the next and last question that I have to talk about with you guys is we're going to talk about question number 45. Question 45 on the first one, I believe, has you working with manganese. And what it's asking for is what the electron configuration is for and how many unpaired electrons does it contain. So for A, Mn2+, the way that I start is I start by writing it out just for manganese. So manganese has a regular electron configuration that's fairly long. It's 1s2, 2s2, 2p6, 3s2, 3p6, then you fill in the 4s before you jump down to the ds. So this is the regular electron configuration for manganese. The noble gas electron configuration would be this, which would be 4s2, 3d5. And this question says that it has a positive 2 charge. Well, that means you're losing 2 electrons. You always lose electrons that are furthest from the center of the nucleus, which are the valence electrons. And the valence are electrons here in the 4s orbital. So if you're losing 2 electrons here, you have to remove them from the highest principal quantum number. Remember that 4 That's the energy level, otherwise what we refer to as N, the principal quantum number. So these get removed, so your electron configuration is Ar3d5. Now the question's asking for how many unpaired how many unpaired electrons there are. So the way I do it is I draw the boxes. So D, we have 5 boxes. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Barely squeezed in. So 5 electrons, I'm going to start filling it in. 1, 2, 3, 4, 5. Holy smokes. We have a total of 5 unpaired electrons. Alright, now let's do B. So B in this problem is talking about silicon with a -2 charge. Silicon's long electron configuration is 1s2, 2s2, 2p6, 3s2, 3p2. If I'm going to do it noble gas configuration style, I've got the Ne, and then it is 3s2, 3p2. Okay, -2. You add electrons into the highest energy level. We're talking about the third energy level. In particular, we're going to add them onto the P. So it is Ne, 3s2, 3p4. That's the Si2 minus. What I wrote above was just silicon. All right, now I got to write out the box notation for this. So for the S, it's 1 box. For the P here, it's a total of 3 boxes. 1, 2, 3, 4. How many unpaired electrons? 2 unpaired electrons, and that's the correct answer. If you guys have any other questions, please let me know. The self-check quiz will be up shortly. Thank you.